Today we're going to start special factoring. And when we do special factoring, we're still talking about trinomials and binomials, but there's some special cases here. I want you to notice that this and this can be square rooted, okay? That's what's special about this. In this case down here, what we have is a cube root minus a cube root, and that is another special case. So the first thing I'm going to do is I'm going to try to solve it just like we did in the last section. So I'm going to say AC equals 100 and B equals negative 20. So that means the two numbers I'm going to split with are negative 10 and negative 10. Now I'm splitting the middle term and then I'm factoring by grouping. So I look at the first two and I say I can take out a 2x and that leaves me with 2x minus 5. Now I can take out a minus 5 and that leaves me with 2x minus 5, which is great. That means I sounded very repetitive because I ended up with 2x minus 5 and 2x minus 5. So this is a special case because if you notice that it was a perfect square, you could just jump right to the answer. And that's because this is 2x and this is 5. And then if you put 2x and minus 5 together, you end up getting this pattern. Perfect squares end up with a pattern, and it looks like this. So let's look at number 2. If we look at number 2, we're going to see it also has a pattern, the same one. And this time it's going to be 7x and 3y squared. Because when we multiply those together, we get 21, and 21 times 2 is 42xy. Notice I wrote it squared like this, but it's the same as if I wrote it like this. Don't let it throw you off, just having the different notation. Let's take a look at number 4. Number 4 is actually a perfect cube and a perfect cube. Number 5 is also a perfect cube and a perfect cube. The difference is that number 4 is subtraction and number 5 is addition. In either case, we're going to use the sum and difference of cubes formula. Sum and difference of cubes is not too bad. What we're going to do is we're going to use this part right here. If you remember it, I always remember it with SOAP, okay? But in any case, I'm going to first identify A and B. So in this one, A is X and B is 2. And then we say X minus 2, same. And then we do X squared minus plus 2X plus 4. Same, opposite, always positive, and so I end up with that as my answer. And that's done. Number 5, we'd use the same shortcut here. The A, if we cube root the first part, we're going to end up with 5x, and the B is just going to be y. Okay, so that means our formula is going to be 5x plus y. Why is it plus? Because it starts out being the same as what it started with. And then we square the first one, so 25x squared. We multiply them together, plus 5xy. And then we square the last one, plus y squared. And we always go same, opposite, always positive, which means this middle sign here needs to be a minus because it has to be the opposite. If we take a look at number 3, people start to get confused because they go, oh, that's a fourth. I can't do a fourth. But what I want to do is I want to try to use the difference of squares. So I just want to square root the top and square root the bottom. Because if I could square root it, then I could split it into two things that one's plus and one's minus. And I can do that because it's going to be 4x squared minus 9 and 4x squared plus 9. Now, the difference of squares is a thing, but the sum of squares is not. So this is done. But this one can go a bit further. We can say 2x minus 3 and 2x plus 3. So to pull the last thing down, we get 4x squared plus 9. I got one last one for you. And that's number 6. Number 6, I've really used too much space, but we can cube root each of these, even though it's to the 6th. The cube root of 64 is 4, and the cube root of 27y to the 6th is 3y squared. And so if I start to pull this apart, I end up with 4 minus 3y squared, and then 16 minus, or plus, because we do the opposite sign. We multiply them together, so we get 12y squared, always positive, plus 9y to the 4th. One last look is to say, can I go any further on this? And the answer is no, so that is my final answer.